You know, when you look up at the night sky, those stars, they feel so permanent, don't they?
They really do. Like
Yeah,
they've just always been there forever.
exactly. But the truth is, well, quite different. Every single one is actually on a clock, a finite timeline.
It's a huge contract, isn't it? And stars, well, much like living things, they have these incredible life cycles, beginnings, middles, and sometimes really dramatic ends.
That's what we're diving into today, right? This whole journey.
Yeah, the whole cosmic story dictated by these two sort of fundamental forces, gravity pulling everything in,
Relentless.
and then nuclear energy pushing everything out, immense power.
Okay, so we're unpacking the lives, the deaths, sometimes explosive deaths of stars. And this isn't just, cool space facts.
No, not at all. Understanding this stellar evolution is fundamental. It basically tells us where all the stuff around us comes from.
The elements, right? The
Yeah.
building blocks of planets, of us.
Precisely.
Yeah.
Including us. So for anyone listening, maybe prepping for exams like the UPSC where you need that solid science background, this is really core knowledge. It helps understand our universe.
Absolutely crucial context.
Yeah.
And it all hinges on that balance you mentioned.
This constant push and pull,
Yeah.
gravity trying to crush the star, nuclear fusion in the core pushing back. That balance, it decides everything. How stable it is, how long it lives.
And it's wild to think we didn't always know what was powering them. What was the fuel?
Right. For ages, it was a mystery. Until 1938, Hans Bethe.
Oh, the train story.
Yeah, apparently he figured out the basics of nuclear fusion in stars while on a train to Ithaca.
Just casually solving one of astrophysics' biggest puzzles on his commute.
Pretty much.
Yeah.
Won him a Nobel Prize eventually. It was the aha moment explaining how stars shine.
Incredible. So that discovery was key. And you mentioned the star's fate depends on its mass.
Mass is critical. Once that nuclear fuel runs low, what happens next is dramatically different depending on how big the star was to begin with. Let's start with stars more like our sun, average size.
Okay, so our sun right now, middle-aged, steadily burning hydrogen into helium in its core.
Yep, that's the main sequence phase.
Yeah.
Very stable, lasts for billions of years. Our sun's been doing it for about, what, 4.5 billion years already?
Right. But that hydrogen in the core, it won't last forever.
Exactly. Eventually it runs out. And when
Yeah.
that happens, gravity starts winning the tug of war. The core contracts.
And gets hotter.
Much hotter. Squeezed by gravity, it heats up incredibly until it hits around 100 million Kelvin.
100 million. That's hard to even imagine.
It is. And at that point, something new happens. Helium nuclei, the ash from the hydrogen burning, they start to fuse.
Into carbon and oxygen.
Into carbon and oxygen, yes. And also, just outside this now helium-burning core, there's a shell of hydrogen that gets hot enough to start fusing too.
Ah, so fusion is happening in two places now.
Kind of, yeah. You've got helium fusion in the core and hydrogen fusion in a shell around it. This shell burning pumps out a lot of energy.
And that pushes the outer layers out.
Way out. The star swells up enormously, becomes red giant.
Bigger, brighter overall, but the surface cools down a bit, making it look reddish.
Exactly. Vastly larger.
So our own sun, billions of years from now, will do this. Become a red giant.
Yep. In about 5 billion years or so, it'll swell up, possibly engulfing Mercury and Venus, maybe even Earth.
Whoa. Okay, that's a pretty dramatic future for the neighborhood.
It is. But this red giant phase isn't the final act. Eventually, the star can't sustain fusion anymore.
What happens?
The outer layers, they just sort of drift away, gently puffed off into space.
Forming those beautiful planetary nebulae we see pictures of.
That's them. Gorgeous clouds of gas and dust. The name's a bit misleading. Nothing to do with planets forming. It's just the star's old atmosphere.
Gentle. Okay,
Yeah.
so not a big explosion for stars like the sun. What's left behind?
What's left is the core, an incredibly dense, hot remnant called a white dwarf.
Mostly carbon and oxygen, you said?
Primarily carbon and oxygen. It's tiny, maybe the size of Earth, but it contains maybe half the sun's original mass squeezed into that small volume. Extremely dense.
And that's the end for most stars.
For about 95% of them, yeah. They become white dwarfs. Our sun will too. It'll just sit there slowly cooling down, radiating away its leftover heat over billions, trillions of years, fading out.
A quiet dimming. A stellar retirement.
A very long, quiet retirement.
But wait, even white dwarfs have a limit, right? They can't just get infinitely massive.
Yes. That's where Supernovae Chandrasekhar comes in. Brilliant work.
Tell us about that.
Well, back in 1930, he was on a ship traveling to England, and he did the calculations. He figured out there's a maximum mass a white dwarf can have and still support itself against gravity.
Using what? Quantum mechanics?
Using the principles of quantum mechanics, yeah.
Mm-hmm.
Specifically, electron degeneracy pressure. He found that if a white dwarf gets heavier than about 1.4 times the mass of our sun...
The Chandrasekhar limit.
That's the one. Above that limit, gravity overwhelms that pressure.
Yeah.
The white dwarf can't hold itself up anymore. It collapses.
And that discovery wasn't immediately accepted, was it?
No, it faced quite a bit of resistance initially, even ridicule from some prominent astronomers. But Chandrasekhar was right.
And it won him a Nobel Prize, too, eventually.
It did. And it was absolutely foundational. It paved the way for understanding what happens next, neutron stars, black holes. It showed there was this critical tipping point.
That 1.4 solar mass number, it's like a fork in the road for stellar death.
A crucial fork. Below it, quiet fading. Above it. Well, things get much more interesting and much more violent, especially for stars that were born much bigger than the sun.
Okay, let's go there. The massive stars. You said at least 8 times the sun's mass?
Yeah, roughly 8 times and up. These are the real heavyweights.
And because they're so massive, the gravity is much stronger. The core gets much, much hotter.
Unbelievably hotter.
Yeah.
Billions of degrees Kelvin in the core. Orders of magnitude hotter than the sun's core.
Wow, and that lets them fuse heavier elements.
Exactly. They don't stop at carbon and oxygen. They can fuse carbon into neon, then oxygen into silicon, then silicon into iron.
So it's like a series of fusion stages going up the periodic table.
Like layers of an onion, yeah. Each stage requires higher temperatures and pressures, and each stage happens faster than the last. Hydrogen burning might last millions of years, but silicon burning might only last a day.
A day. That's incredibly fast. But you said iron is the end of the line.
Iron is the absolute end of the line for fusion releasing energy. Fusing elements lighter than iron releases energy, pushing back against gravity.
Okay.
But fusing iron, or anything heavier, actually consumes energy. It takes energy in instead of giving it out.
Uh-oh. So the outward pressure just stops.
It vanishes instantly, well, on astronomical timescales. The core loses its support against gravity's crushing force.
And what happens?
Catastrophic collapse. The core implodes in on itself in a fraction of a second.
A fraction of a second. The entire core.
The iron core collapses violently. The outer layers of the star, which were still falling inwards, crash onto this suddenly rigid, super dense core.
And bounce off.
They rebound violently, combined with a massive blast of energy carried by particles called neutrinos escaping the core. This drives a shock wave outwards through the star.
And that's the supernova.
It is a supernova explosion,
Wow.
an absolutely titanic blast. For a few weeks, that single exploding star can outshine its entire host galaxy.
Brighter than billions of stars combined. Just staggering. What's left after that explosion?
Depends on the mass. The collapsed core becomes either an incredibly dense neutron star.
Like a city-sized object with more mass than the sun.
Exactly. Made almost entirely of neutrons packed tightly together. Or if the original star was massive enough, even the neutron pressure isn't enough, and the collapse continues.
Forming a black hole.
Forming a black hole where gravity is so strong that nothing, not even light, can escape.
So these incredibly violent deaths, they're not just spectacles, are they? They actually do something crucial.
Oh, absolutely crucial. Remember how we said fusion in stars only goes up to iron?
Right.
Well, where do all the heavier elements come from? Gold, silver, platinum, uranium, iodine, which we need.
Where do they come from?
They are forged in the unimaginable heat and pressure and neutron flux during a supernova explosion.
So the explosion itself creates them.
And also in other events, like colliding neutron stars, which are now thought to be major sources of the very heaviest elements, like gold. But supernovae create and distribute a huge range of them. The conditions are just right: intense heat, pressure, loads of neutrons flying around to rapidly build heavier nuclei from lighter ones.
And then the explosion scatters this newly made stuff everywhere.
Exactly. It blasts these heavy elements across the galaxy, seeding the interstellar medium, the gas and dust clouds between stars.
So future stars and planets form from this enriched material.
Precisely. Those clouds collapse, form new stars, new planets, and those planets now contain elements like iron, calcium, silicon, gold, all the things forged in previous generations of stars that died.
So the iron in our blood,
Came from a supernova.
the calcium in our bones.
Verged in the heart of a dying star, likely a massive one. It's not just poetic, it's literally true. We are made of stardust.
That is profound, truly profound. Now, you also briefly mentioned another type Ia supernovae, with white dwarfs.
Right, those are a bit different, but also important. They happen in binary systems, two stars orbiting each other.
Okay.
If one star becomes a white dwarf and its companion star is close enough, the white dwarf can pull material off the companion.
Accretion, right.
Yes, it steals gas, mostly hydrogen and helium, from its partner. If it pulls enough material to push its own mass over that Chandrasekhar limit.
That 1.4 solar mass limit again?
Exactly. Once it crosses that limit, it can't support itself anymore. But instead of just collapsing further like a massive star core, the whole white dwarf undergoes runaway thermonuclear fusion. Basically, the whole thing ignites at once.
Kaboom.
A complete catastrophic explosion. The white dwarf is totally destroyed.
And these are useful for astronomers.
Incredibly useful, because they happen when a white dwarf hits that specific mass limit. They all explode with roughly the same peak brightness.
Like standard light bulbs.
Exactly. Standard candles, we call them.
Yeah.
By measuring how bright they appear, we can figure out how far away they are. They're like cosmic mile markers, helping us measure the scale and even the expansion of the universe.
Amazing. A dead star used as a measuring tape. And they also spread heavy elements, too.
They do. They contribute significantly to the iron abundance in the universe, for instance.
So it seems like whether it's the quiet fade-out of a sun-like star or the spectacular blast of a massive one, stellar death isn't really an ending.
Not in the final sense, no. It's more like transformation. It's a critical part of this huge cosmic recycling program.
Birth, life, death, and then the raw materials for new birth.
Exactly. The death of stars provides the essential ingredients for the next generation of stars, planets, and maybe even life. It's cosmic renewal, driven by stellar death.
Okay, so let's just summarize the key points, especially for, listeners maybe studying for UPSC or just wanting that clear picture.
Sure.
Stars have finite lives. Their path is set by their initial mass. They stay stable, balancing gravity, pulling in, and fusion pushing out.
Right.
Sun-like stars end relatively quietly, puffing off outer layers to form a planetary nebula, leaving behind a white dwarf that just cools down.
The quiet retirement.
But massive stars, more than 8 times the sun's mass, they go out with a bang. They fuse elements up to iron, the core collapses.
Supernova, leaving behind a neutron star or a black hole.
And crucially, these deaths, especially supernovae, are where most of the elements heavier than helium and lithium, particularly those heavier than iron, are made and scattered across the universe.
Forging and distributing the building blocks of everything.
Including us.
Absolutely. It really highlights how connected everything is, doesn't it? From the tiniest atom in your body to the biggest star exploding light years away, it's all part of the same grand cosmic story.
It definitely puts things in perspective. So for all of you listening, whether you're the dedicated UPSC aspirant needing to grasp these fundamental cosmic cycles, or just someone fascinated by the universe, understanding stellar lives and deaths really gives you that essential backdrop. You see where the materials that make up Earth and us actually originated.
And maybe something for you to think about. How does knowing this, knowing you're literally made of elements forged in stars, change how you view your place in the universe?
That's a deep thought to end on. If you found this deep dive into stellar life cycles helpful and you want more explorations of the science shaping our cosmos, please do like this, subscribe for more content, and definitely leave a comment. Any questions, thoughts? We'd love to hear them.
Yeah, let us know what you think.
We drew on some great material published in the Indian Express for today's discussion. Thanks for joining us on this journey through the stars.